Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum warahmatullah. Welcome to the third lecture of week 7. So in this week we were discussing chapter number 20, and that is sheet metal working. So in the last lectures we had discussed the first type of sheet metal process, that is the sheet metal cutting, which includes the blanking and the punching. Now in this lecture we are going to discuss the second type of sheet metal, that is known as the sheet metal bending. So what the sheet metal bending is? Sheet metal bending is simply straining any sheet along an axis. Like let's suppose we have an axis here. So the straining the sheet along an axis, along a straight axis, that is simply termed as the sheet metal bending operation. So during this bending operation, the metal on the inside of the neutral axis, if you see closely here, during this bending operation, the metal on the inside of this neutral axis, the inside this area of the neutral axis, right? And so the metal on the inside of the neutral axis is experiencing compression, while the metal on the outside of the neutral axis experiences tension. The metal on the outside here, it experiences tension. It is in a stretch position. Then metal on the outside and the metal that is inside the neutral axis, that is under the compression. And this bending is obviously, it's a plastic deformation, it's a permanent deformation. So we stress it enough so that it takes a permanent deformation in this way. But this bending operation doesn't affect the thickness of the sheet. It has little or no effect on the thickness of the sheet, right? So what is the sheet metal bending operation? Sheet metal bending operation is simply straining a sheet along a straight axis, straining a sheet along the straight axis, right? So we have a neutral axis. So the metal on the inside of the neutral axis, it is under the compression, while the metal on the outside of the neutral axis, that is in the tension. And this bending operation doesn't affect the thickness of the sheet. So what are the two types of the sheet metal operations? Sheet metal bending operation. So primarily we have two major types of sheet metal bending operation. The first one is known as a V bending, and that is performed on V dies. The V dies you can see here. And the second one is the edge bending, and it is performed on wiping dies. So in the case of the V bending, the sheet metal is bent between a V-shaped punch and die. So we have a sheet metal and we have a V-shaped die and a V-shaped punch. So the sheet metal is strained between the V-shaped punch and die. It is used for low production and it is performed on a press brake, right? And they are somewhat inexpensive. While in the case of the edge bending, we have an additional feature that is known as a pressure pad. The purpose of pressure pad is to hold the sheet metal for the bending by the punch. So it involves cantilever loading. Cantilever loading means it is supported at one end while free at the other end. So it involves cantilever loading of the sheet metal. A pressure pad, this one, is used to apply the force Fh, that is the holding force, and against the die. We have the die here. So the pressure pad is applying the force against the die, and the punch exerts the force. The punch exerts the force to yield the sheet metal. So the maximum amount of bend that can be created using the edge bending, that is the 90 degree. So it can bend the sheet along the 90 degrees, right? But there are some special wiping dies where we can have some more bending than the 90 degrees. While in the case of the V bending, we can bend more than 90 degrees in this case. So if we move towards the analysis of the bending operation, so some of the important terms of sheet metal bending are identified here. We have a sheet with the width of W, and we have the thickness, that is T. We have the internal radius of the bend, right? We have the neutral axis here. So the inside is under the compression it's shown here, and the outside is another tension. If we strain the sheet metal along axis, so the angle it is strained, which is also known as the bent angle, the angle along which by which it is strained, which is also known as the bend angle, that is known as the alpha, and the remaining is known as the alpha prime. So we have alpha plus alpha prime equals to 180 degrees, and we have the bend radius r, as is shown here, right, and the width of the part, that is equals to w. So one of the important term in the case of the sheet metal bending is the bend allowance. What the bend allowance is: if the bend radius, this r, if the bend radius is very small comparative to the thickness of the sheet, the metal tends to stretch during bending. So when we bend it, there's some stretching experience here. So let's suppose if we have a sheet like this, if we have a sheet like this one, and there is a, if you draw a neutral axis, so there is some length of neutral axis, like length of neutral axis, and if you bend the same sheet, at a certain radius, if you bend the same sheet at a certain radius, let's say r, so within our neutral axis would be like this one, right? So the length of the neutral axis before and after the bending should be same, but that's not the case. If the radius for the small bend radius, there is some stretching along this bend, so because of that the length of the neutral axis increases during the bending operation. So in order to estimate that bending in the final part, we have a term, we have an allowance that is used to calculate. So the bend allowance is simply the stretching of the neutral axis, that is a length by which the neutral axis has increased, right? So bend allowance is equals to AB 2 pi equals to 2.2 alpha by 360 into the bend radius plus kVA into the T, where kVA is a stretching factor. kV equals to 3. So we have bend angle, as we have already seen. R is the bend radius, T is the stock thickness, and we have the kVA equals to stretching factor, you can say. Right. So if R is less than twice of the stock thickness, if you're bending the sheet such that the radius of the bend is less than twice of the stock thickness, then the value of kVA will be equals to 0.33, and if R is greater than twice of the stock thickness, then value of kVA would be equals to 0.5. Then there's another phenomena that takes place in the case of the bending operation, that is known as a spring back. So in this phenomena, when the bending operation is being performed on the sheet metal, when this punch is removed at the end of the deformation, so because of this elastic energy within the material, it tries to regain its original shape. So let's suppose we have bent the sheet metal at an angle of alpha prime b, but once the pressure pad is removed, let's say the alpha prime b was equals to 80 degrees, but once the pressure pad or the punch has been removed, it has the angle has been changed to alpha prime, which might be uh, 95 degrees, right? Because the angle has somewhat increased, because it tries to regain its original shape, which was the flat sheet metal. So this phenomenon is known as a spring back. So how to calculate it, the spring back? So it is illustrated using this formula. The spring back equals to alpha prime minus alpha prime t divided by the alpha prime t. So in this case, alpha prime is the included angle of the sheet metal part, while alpha prime t, that is included angle of the bending tool. And the angles are obviously in the degrees. But how to overcome this problem of the spring back, because it is obviously disturbing our dimensions, and this spring back increases with the increase in the modulus of elasticity of the material. Obviously, if you're using material which has a higher modulus of elasticity, so there will be a higher amount of spring back in that material. So to compensate the spring back, primarily there are two methods to compensate the spring back, and the first one is known as the overbending, and second one is known as the bottoming. So overbending, as the name suggests, we slightly overbend the material. Let's say if we want to achieve bend angle of, let's say, 92 degrees, right? So what we do, we will bend it at an angle of, let's say, 86 degrees. So because of the spring back phenomena, once we achieve the angle of 86 degrees, so because of the spring back phenomena, once we achieve the angle of 86 degrees and the punch has been removed, it will try to regain its original shape, so the bend angle will increase and we will finally achieve the angle of 92 degrees. Obviously this calculation is based on the many factors, especially the Young's modulus of the material we are using, right? Second method is bottoming, and what the bottoming is, it involves squeezing the part at the end of the stroke. So once we have reached the end of the stroke, we will slightly squeeze the part along this edge, along this end. So this will plastically deform the sheet metal at the certain angle. So it's like a mechanical interlocking once you achieve the shape, once you achieve the bend angle. So these are the two ways to calculate to avoid the spring back phenomena. The first one is overbending. We will slightly overbend the material so that once the pressure pad has been removed, the punch has been removed, it will try to regain its original shape, so we will ultimately have the desired angle. And second one is the bottoming. We will squeeze the sheet metal at the end of the stroke, right? What we do, we squeeze the at the end of the stroke. So it will kind of a mechanical interlocking for the material. And that's all for the spring back phenomena. Now the another term that is important for the sheet metal bending, that is the bending force. The force required to perform the bending depends on the geometry of the punch and die we are using, and the thickness of the sheet, the strength of the material we are using. So the bending formula. Let me erase this one. So we have the first formula, that is the bend allowance. What was the bend allowance? That was the stretching along the neutral axis. The second one was the bending, the spring back phenomena, and the third one is the bending force, that is equals to F KBF into tensile strength of the material into the width and the stock thickness square divided by D, right? So where D is the opening dimensions, D is the die opening dimensions, right? And T is the tensile strength of the material, and KBF is the bending force coefficient. So for the V bending, we have KBF equals to 1.33, and for edge bending, KBF equals to 0.33. These are the all required terms for the sheet metal bending operation. Now we'll move towards some numerical problem for the sheet metal bending, and then we will see some specialized type of the bending operation. So in this section we are performing the numerical problem. So what it says, a sheet metal blank is to be bent as shown in the figure here. The metal has a modulus of elasticity that is equals to 205 10 exponent 3 megapascals, and the yield strength of 275 megapascals, and the tensile strength of 450 megapascal. Determine the starting blank size, part A, and the part B is determine the bending force if a V die is used with the die opening dimensions of 25 millimeter. As we have just seen, the die opening dimension, that is equals to D. This is the D. So if in this figure, if you see here, we have the dimensions, that is 38 on this side, 25 on this side. We have an included angle of 120 degrees, so obviously the remaining angle is 60 degree, and we have the stock thickness of 3.2 millimeters, and the width of the sheet is 44.5, right? So let's start with the starting blank size. So we know that the width is equals to 44.5 millimeters, and the length, total length would be 38, this plus this bent area, the bent allowance we have seen in the previous slides, plus 25. So we have 38 plus the bend allowance, the stretching on this bent area, plus 25. So, and we have the included angle of 120 degrees and the external angle of 60 degrees. As we know that we have R equals to 4.75 millimeter, while the stock thickness is equals to 3.2 millimeter. So R is less than 2T, so the value of KBA would be equals to, the bend allowance constant would be equals to 0.33, right? So this is how we can calculate the AB. So AB equals to 2 pi in alpha by 360 into R plus KBA into T, and that is equals to 2 pi, we have the alpha equals to 60 by 360 into the R, we have R equals to 4.75 plus 0.33 into what is the thickness, that is 3.2. So the bend allowance would be equals to, that is equals to 6.08 millimeter. This is the bend length. Now the part B is about the bending force, and as we know, the bending force is equals to F equals to KBF into the tensile strength into WT square, that's width into the thickness square, divided by the die opening dimensions. So if you write it here, that is F equals to KBF, as we have a V die operation, so the KBF would be equals to 1.33 into the tensile strength, that is 450 megapascals, into the width, that is 44.5 into 3.2 square, whole divided by 2.5, that is as it is 25 millimeter, so that is 2.5. So the total force is equals to 10,909 newtons. This is the value of the force. So beside the general operations of the bending, there are some specialized operation, that is known as other bending operations. So we have 6 different types of the bending operation based on the geometry of the product. So we have 3 different types of the bending operation. The first one is known as the flanging, then we have the hemming and the seaming. And we have discussed this, what the seam is, in the lectures of the bulk deformation and the curling. So there are some specialized type of the bending operation. What is the flanging? Flange is to bend something at an angle of 90 degree. That is simply called a flange. For the sake of assembly, you can say, you must have studied in the subject of fluid mechanics the flange or the flange joint. So we have a pipe that is bent at an angle of 90 degree from the end, like this. So the pipe that is bent at an angle of 90 degree from the end, like this one. So this is called a flange. So we have the bolts from both ends, so that is called as a flange contact. So flanging is bending operation in which an edge of a sheet metal is bent at an angle of 90 degrees, like in this case it is bent at an angle of 90 degrees. That is called as a flanging operation. Flange can be formed over a straight bend axis, as illustrated in this diagram, along the straight axis like this one, or along the bent axis like this one. So they both are flange the flange bending. The second one, that is called as the hemming. It involves bending the edge of the sheet over on itself. So this one is the hemming, that bending the sheet metal on itself, like this one. If in more than one bending step, so it is not necessary that we have to bend this or we have to perform the hemming in a single step. It can be performed in multiple steps. The third one, that is known as the seaming, is a somewhat related operation in which two sheets metal are assembled like this. They are joined along a line. They are assembled by mechanical bending. That is known as the seaming operation. That is a bending operation. And the last one is the curling operation. It is also known as the beading. It is also known as the beading operation. So it forms the edge of the part into a roll. It forms the edge of the part into a roll or a curl. That is simply the curling or the beading operation. The purpose, especially for the hemming one, its main purpose is for the safety, to increase the strength along this area of the sheet metal, or to have some aesthetics, to make the product look good. So that's why you perform the hemming one. And there are some other miscellaneous objectives which you achieve using the this specialized type of the bending operation. So that's all for this lecture for the sheet metal bending. In the next lecture we are going to discuss the third type of the sheet metal bending, that is the last type, that is the drawing or the deep drawing operation. And then we will discuss some specialized sheet metal operation that are performed on mechanical by on the rubber tools or some other tools.